the whole world at our feet, watching seasons change. Our roads were lined with adventure, mountains in the way couldn't keep us from the sea. Here we stand, open arms. This is home where we are, ever strong in the world that we made. I still hear you in the breeze, see your shadows in the trees, holding on.
Okay, good evening everyone, and apologies for being late. Actually, I decided to change my USB hub, which I have next to my PC, to upgrade it because it was an old USB 2.0 USB hub, and I usually connected my microphone and my webcam to it. And it worked really well, but the exterior became a little, you know, the type of exterior they use, like the rubber feeling, like after a few years it gets really messy, and if dirt, like dust, is attached to it additionally, it doesn't really work. So I decided to change it, and I changed it to an IC box one, a nice one, USB 3.0, so not a like super new one, 3.1, but 3.0. With switches so I can turn on and turn off devices, and it worked with my printer. Doesn't really work with my microphone or my webcam. So it worked like for 30 seconds with my webcam, and then it failed. Yeah, so that's the reason I'm late. I actually had to hook up my microphone to my keyboard because I have a USB 2.0 hub in my keyboard, and grab a USB extension cord to hook up the webcam to my PC directly. Yeah, hardware problems, the usual. Anyway, so good evening officially. Today my moderator is KrzaQ. So if you have any questions during the live stream about the topic or about something else which I could potentially answer, then do ask KrzaQ. His nickname is right here. If you are on YouTube chat, do ping KrzaQ, using the @ sign, and then select his nickname. Or if you're on IRC, you can actually do !Q, and that also puts a question in the panel where I can see it. Since, as you know, I'm sometimes looking at the chat, but not always. Yeah, so that's it. Today's topic is going to be async and await in Python 3. I actually never used it before, like literally never. And it's a topic like a lot of you actually ask me about, and I have no idea about it. So I want to try and figure out what is it, how does it work? Because this is my streams are usually pretty low level, pretty internal. So I'm going to figure out how it works, and not really what to use it for. So if you're looking to learn like how to use it properly, or how to use it, what to use it for, then yeah, probably like you will have to go to another YouTuber, I guess. If you know already async and await in Python, then I guess there are other more interesting things you could do, because you will not learn anything new today. Yeah, I will probably try to emulate them. Like I'll probably go like this. I'll start with what I think they are useful for, and I'll try to use that in Python 2. In Python 2 there is no async and await, by the way. This is from what I know as syntax sugar added later on. And then I'll try to adapt that syntax sugar from the new Python, from Python 3, into whatever I write in Python 2. And then there is this nice async IO library. At the end I'll try to use it, and I'll try to figure out what is it good for. So that's the plan. We'll see how it goes, but again, it will be just me trying to figure out how it works. It's not a stream where I'm telling you how to do things, because I have no idea. I have no idea about async and await in Python. That being said, I do know about coroutines. I do know about fibers. I do know how they are implemented in low level in assembly. I do know what they are useful for. I did use them in the past. So I do know that. I do have the theoretical background for it, and I will yeah, probably like also try to introduce you into it if you don't know by any chance. Anyway, so I guess it's like some of my usual viewers are playing hack.lu CTF. It's I usually like hack.lu CTF is pretty awesome, and this year it seems to be the same. I didn't have too much time to play, in all honesty. I solved one task, which wasn't super hard, but it was quite fun actually. We might chat about it later on. As in not during the CTF obviously, but like next week or in 2 weeks. Speaking about next week there will be one live stream, like the English live stream on Wednesday evening, but then following week there won't be any live streams, or will be only a Polish one. But I might have a really cool mission / competition for you that some folks are working on. But let's chat about it when it actually happens. So yeah, that's it. As usual, let's start around, I guess, 15 past. So if you have any questions, now is a decent time to ask them. So far, there is one question. The questions should be displayed here. Przemek writes, don't you think frequent firmware updates caused by security vulns and firmware are too risky and too hard for ordinary non-technical person? Shouldn't it be made easier and safer? So that depends. I guess what you mean by the question is like there's always a chance to break a device. My feeling is that in several years ago, that was a typical problem. Like you just threw a coin and like know if your BIOS is going to break or no. Then it got better, and it got even better now. So if a device is actually made with some, like for example, flash backup for the previous version of the firmware, so if you break the device and then it still can actually just reflash it itself with the backup, that doesn't sound too bad actually. So it depends on the device, right? If the device is made well and there is no chance of breaking it, then it doesn't really matter, right? I don't see risk in updating the firmware, assuming obviously that the firmware update is done correctly, there is a proper signature check, and so on and so on. So yeah, that's it. If you have a device which you kind of figure out that it might break when updating, then I agree it might be risky, but yeah, like contact the manufacturer, ask them about it. Like maybe the process of updating the firmware is actually bulletproof. Okay, surprisingly, no more questions. Cool. Let me think. I guess I need to... Oh, wait, let's go through usual web pages. Starting with this one. This is KrzaQ's blog, my moderators. And yeah, it's dev.krzaQ.cc. This is how you actually spell his nickname. It's KrzaQ, not KrzaQ. It's not KrzaQ. Yeah, KrzaQ. Anyway, do check it out, though KrzaQ is... you owe us a post. There was actually a post on the Polish side of his blog, DSP, that's a mistake. Yeah, this is a Polish side of the blog, and he actually updates it. So yeah, if you're on the chat, totally ping KrzaQ about updating his English post as well. Apart from that, I'm trying to figure out if there are any updates. I probably said this 100 times, but there is this conference I'm co-organizing in Warsaw in Poland in November. The talks will be mostly in Polish, but there will be a simultaneous translator present. And there will also be the Dragon CTF finals during the conference for open for conference attendees. So if you have a conference ticket, then you can totally play. 32 days, so 1 month. And yeah, check it out if you're interested. I guess that's about it actually for updates today. I see there is another 2 questions, and we have still about 2 minutes left. So let's go. What happened to YouTube today? Was that security issue or just platform error? I actually don't know. I have no idea. I seen on like some web pages that hey, YouTube went down, but I didn't see. And I didn't follow up like internally what went wrong, so I have no idea. I don't expect a security error. Yeah. What can be improved in Python for the next version? I don't know. I don't know because I'm not fully up to date with Python. What I would love to see in Python is, well, I guess we're getting there with Python, right? The thing I always miss with Python is like strong typing. It doesn't have to be super strong, but when I get a parameter in a function, I would like to tell Python that, hey, this has to be a string. And if it's not a string, then like just throw an exception because it's not a proper usage of this function. Because if I don't do that, then instead of like writing str and then name of a variable, I have to include an if, like a whole line of type checking inside, and that's even worse in Python 2, where you actually had Unicode strings and normal strings, and you operated on them almost identically. So you usually group them, or like int and long, which is even a better example because, yeah. Anyway, and that being said, that already changed. Like in Python 3 already you can enable annotations for types, so you can write like int something. But there's actually a proper syntax for it, and what I'm saying right now is not the proper syntax. But it's only annotation. It was only annotation. As in, you couldn't really, like, it didn't change anything. You could still pass a string to a function which expected int, and that was all fine. You actually had to include some library which would do the checking for you, which internally, I guess, was like getting a list of functions, the annotations, and then wrapping the functions with some checkers and so on. So that was, I expect, a complicated process. But that's also improving. Also, the syntax is improving on what you can do with these annotations. So that was one thing I missed in Python for writing, like, you know, more production quality code. If you write production quality code in Python, there are some problems with a global interpreter log. Yeah, I guess that's another part of the answer is like, if we could have proper threading in Python, but you have, because currently you can in Python have multiple IO blocking threads, because there are two types of threads, right? There are IO bound threads and there is CPU bound threads. The IO bound threads are threads which commonly block an operation like waiting for data, sleeping, or like sending data, or actually like telling the kernel to send the data and then get back when the data is already sent. So the thread is sleeping for that time when the data is being sent. So these are IO bound threads. They don't do too much math. And that's fine for Python. That works actually really well in Python. Now there is the other type of a thread which is more for calculations, the CPU-bound threads, which where you have like multiple cores, for example, on your CPUs. Current CPUs on the market have like 10 and 18 cores, right? So you'd like to use them. And yeah, so you create a couple of threads, and every thread does some calculation. Like, I don't know, brute forcing of a hash for the sake of example. And the problem in Python is that doesn't really work because only one thread will have the lock and the other threads will have to wait until the lock is let go. So that's not ideal, and that's obviously not a language problem because that's the default implementation problem. But given that almost everyone uses the default implementation, I would love to see it fixed in CPython. So yeah. If we're talking about CPython next version, then yes, please fix that. And workarounds like multiprocessing are like just workarounds. Cool. Do you like the new Chrome theme? Yeah, it's pretty cool. Yeah, KrzaQ just gave me a link to the, I think to the library I had in mind for Python, which you have to use. Yeah, runtime checking for Python, which means you actually have to, oh, there's the syntax example, thank you. Yeah, you actually have to import some library to have type checking, which is kinda not what I would expect, especially if you have the option to give the annotation, but you do not have to give the annotation of a type. Yeah. Stupid question. If I would like to learn Python, should I learn 2 or 3? Good question. Really good question, actually. is like this. For production level code, Python 3, there is no question about it. For CTF stuff, Python 2 is just easier to use. You just create code faster. You do not have to worry about that some functions return a string and some functions return a byte or bytes type and whatever. There is the dot encoding with strings in Python 2, which is way easier to use than whatever codex library in Python 3. And there are some small other details in Python 2 which make it just easier to write ad hoc code. So for CTFs, it's magnificent. Like most of the CTF scene uses Python 2, right? But for production code, I prefer Python 3, unless there are reasons not to use it. So both, both. How to be good at programming to play CTF? How to be good at programming to play CTFs? So it's a good question. Actually, it's like this. Not for every type of challenge in CTFs you need programming skills. But being said, for all the harder problems you need. There's also no question about it, but you do need to write ad hoc code, you do need to write scripts, programs, and so on to solve some problems, because most of the problems on CTFs are not really solvable by hand. So I guess there's only one answer to that, and that program a lot. I mean, program and then program and then program, and after a few years you will suddenly realize that, oh, I actually can code. So yeah, there is no getting away around it. You do have to program a lot to be good at programming. There is no cheating here that, oh, maybe if I do this, I suddenly be like a master level. No, it's like, I guess it's like with languages, right? With speaking languages. And in the end, you have to just sit and learn. And it's the same with programming. The more time you spend programming, the better you will be with it. In CTFs, you use the general programming skills apart from the security part of the CTFs, right? Because that's also a huge chunk. But general programming skills are useful on CTFs if you have the other background. Anyway, so it's already 20 past, so let's do the rest of the questions later on. And now let's try to play with coroutines and other stuff like that. So yield. Yield is the thing we are going after, because yield is at the core of everything in this case. So I guess I'm going to write Python 3 code today, but I do need to create another directory. 64, okay. Surprisingly, I'm not naming my code, my file with the code ASDF today. I'm naming it code. Okay, and I need Python 3. Which Python 3s do I have available? Let's see. I have Python 3.6.2. That's not the newest one, is it? It's probably pretty old. Let's see. Python. Okay. Here we go. And the newest one is Python 7.0. Okay. Yeah, I guess I'm going to install Python 7.0 actually. So, no. That's cool. I don't know. I think it's like 32 bits. I want 64 bits. So one more try. Release candidate. No, I don't want release candidate. So I want this one. Web-based installer, executable installer. Yeah, this should be fine. Okay, so no, don't install this. Just install the 64-bit version. Yeah, I want to go with the newest Python today because I'm not really sure. I think like all the syntax I need is available in 3.6, but just to be sure. So yeah, why is it downloading so long? It's like 25 megs. Anyway. Okay, so yield is I guess the main character in our play today. It's like this. It's actually used for generators, but generators in Python create new fibers. And if you're new to programming on the theoretical level, you might be wondering, hey, what's the difference between a thread and a fiber? Well, I guess like if you're thinking about like a physical object, like a physical thread, then a fiber is what it's made of, right? And that's kind of a decent analogy, actually. It's like this. If you have two threads, like this is thread 1 and this is thread 2, then if you have two CPU cores, then both of the threads are executed at the same time. So this thread is executed at the same time as this thread. Now, a thread usually in low-level terms is has a couple of things it owns. It owns its own thread stack, so there is a thread stack associated with each of these threads. In Python it's different, but speaking of assembly right now, right? And then registry set. Each thread has its own registry set. So yeah, this is a registry set. So you know, like every register is basically cloned in each thread. And if the CPU says, oh, I actually need to do context switch and change which thread is running on the CPU, it archives the registers and like gets another thread's registers, loads them in the CPU registers, and then continues the execution with another thread. That's how context switching works on a really like simple terms. It also has stuff like local thread variables, but it's somewhat related to this, but let's assume that we also add thread local storage or local thread storage. Thread local storage TLS. So yeah, if you're thinking about threads, usually this is what you think about. On some operating systems, the threads might have like different threads might have different privileges. So you can do some stuff from this thread, but you cannot do that stuff from a different thread, which is a pretty weak boundary unless you do stuff right. Anyway, so what happens if you, for example, like let's assume both threads are IO bound, which means they do networking, for example. So and suddenly this thread is waiting for data, so it stops. Like it stops execution here and is now waiting for data, and the kernel of our operating system will actually wake it up after the data arrives. And then like this thread is also at this time point is waiting for data. That means that this threads actually just stopped executing. Obviously, that doesn't mean that the CPU is not used anymore. The operating system says, okay, this thread had its own quant of time, and that didn't use it fully because it went sleeping because it's waiting for more data, which means that I can actually like check the list of other threads. Maybe another thread is already ready to start executing. Maybe another thread was waiting for data, but now the data arrived. So the operating system schedules another thread to run and then runs the other thread as these two threads are sleeping. Now, the problem here is that context switching by the kernel is actually super slow. And that's slow for several reasons, especially if it's a switch between threads which are in two different processes, because that means that well, like for example, on the memory management level, each thread has its own memory space, which means that you need to swap the trees. And that means that your cache, which remembers the mappings of memory, needs to be invalidated because it's not accurate anymore for the other process. Then like the cache which you had in your CPU cache is also probably not valid because suddenly like a different stack, different memory addresses, different content of memory for the same space, which means that the stuff you have in your CPU cache is also invalid on some level and will be evicted probably mostly or fully until you get back to your own thread. Like if this thread wakes up, it will, in the CPU cache, there will be almost no data related to it unless it was like it really receives the data fast. So context switching on the thread level, on the operating system level, is super slow. So do we really have to do context switching on the level of the kernel? Maybe we could do in-process user mode context switching. So if we have like several threads, like user mode threads in our process, maybe we can switch between them. If this one is waiting for data, maybe we can execute another thread which is operating in the same process. That means we do not have to swap the page tables, the page table tree. We do not have to invalidate the cache of the mappings. We do not have to invalidate the CPU cache. We can actually still use it because we are running. Maybe we are not using the same stack, but we are using the same heap. We are using maybe the same data, the same object. So if we could do the user mode switching, that would be actually way better for us because that would be way faster. We could use the quant of time, which is the amount of time given to us by the operating system to run at one time. We can use it better. We can use it to the full extent before the operating system actually like takes the CPU away from us and allows another program to run in the system. So yeah, the concept that I'm describing here are fibers, and a fiber is basically a user mode thread. A fiber has the characteristics which are typical to a thread. It also has its own stack. It also has its own registry set, which when context switching in user mode, we need to archive and then like load again when switching to a fiber. It might have its own like fiber local storage variables, whatever. So it's pretty much a thread, but it isn't a separate execution unit in terms of the operating system or the CPU. So instead of that, it actually, if we see a thread, right? Like let's assume this is a thread. So a thread might run a fiber number one, like fiber number one might be executed here, and then fiber number one says, I need to wait for data, please context switch to another thread. And and by the way, that please context switch to another thread is called yielding. So yield, this is where the term comes from in Python. So then this thread starts to execute the thin scheduler, which is running in thread, which selects another fiber to run, which is, by the way, is on its own fiber. So this is another fiber, like fiber scheduler. And then it selects another thread to run, like for example, another. And this thread is running, and then this thread says, oh, I'm actually going to sleep for 1 second now, so yeah, just like select another thread to use our CPU time. And we again enter the fiber, which is responsible for switching the fibers, and it selects yet another fiber, and I'm running out of colors. Yeah, and then another fiber is run here. So this is fiber 3, this is fiber 2, and then at the end it could also, you know, switch back to, like for example, data is ready for fiber 1, so it could switch back to fiber 1 again. And everything, no fibers are executed at the same time. There's only one thread executing all the fibers. We could have multiple threads executing a group of fibers, but that's also doable, by the way. I don't think there are any hard problems related to that, but that depends on your application design, actually. So yeah, and apart from that, we could have, you know, another thread running and doing its own stuff here, like, I don't know, some calculations or being IO bound or whatever. That's basically the idea of fibers. And yeah, in Python, you can achieve that using the yield keyword. And the yield keyword actually... Oh, there's a good question on the chat. When I'm saying that context switching is super slow, are we talking of how many clock cycles are we talking? It's a good question, actually, because it's like this. It's hard to measure because the time of switching on the kernel level is one thing, but then there are consequences of the switch, being cache entry not found because the cache was invalidated, and so on. That means that the code immediately after the switch will be kinda slow because it will be waiting for the proper data to be loaded from RAM again. It will be waiting for the page tables to be resolved and so on. But strongly depends on the CPU architecture, of course. So it's hard to say. The context switch itself probably is rather fast. I don't know, like few... My guess, this is my personal guess. I would say like 50,000 cycles. Do not quote me on that, do not use that number, but give or take. It might be a little more than that, like depending on RAM access by the scheduler and so on. So that is pretty okay. The consequences of switching makes the code running after the switch rather slow at the initial, unless, you know, until, you know, the stuff is loaded into caches again, and then it can run with full speed. So yeah, and that consequence doesn't happen in case of user mode switching and fibers, but again, user mode switching and fibers can only be done in one process. You cannot switch between processes because that requires the full kernel level context switching. Okay, so let's chat about the yield keyword in Python. ASDF, let's create this. Okay, let's start with generators, because I guess generators are pretty cool things. We can do tell it to yield, and it will actually stop execution of the function. So we can do print asdf, then yield, and print xyz. Now, additionally, we can yield some data. So let's yield 1 and here yield 2. And if we do something like this, I don't know, x in asdf, then asdf is used as the generator, and the 1 and later the 2 will go into x. So if we print x here, we will see that we will basically get asdf, then 1, then xyz, then 2. Print it, and let's actually make sure that happens. But before that, I didn't install Python yet. So to install Python, I do need to copy it to a different directory, because I cannot execute code from my downloads directory, which is, you know, in case I actually download something malicious for, I don't know, like reverse engineering purposes or whatever. I don't accidentally click enter on it. Oh, right, it's Python. It's Python 2 still. I will switch to Python 3 in a second. Okay, customize next. Okay, it's installing. So for now, let's just run it. Yeah, and it's exactly as I said. Now there's a funny thing in Python 2 about this yield and about this function. Let's call the function directly, and you will see that a funny thing will happen. What you might expect it to actually return 1 when you first call it, or 2 when you second time call it, or like at least return 1 for us or whatever. If you are using Python, you know that will not happen, because it will actually return a generator object. And which means that, and that's actually quite funny, because I always thought that it returns the generator object at the first time yield is actually encountered by the code, is executed, right? But please note that asdf was not printed. This asdf is not printed anywhere. Even if you do like, let's remove these yields here, and if you do, if false, this never gets executed, yield, we will still get a generator. So in terms of Python, whenever you actually use the keyword yield in a function, Python 2 will know that, and Python 3 the same, will assume, yes, this is a generator function now. And a generator function always, upon calling, returns a generator object, and is not executed until you actually use the generator. So if we take the asdf and then use, how was it, funccode.co flags, I think. And let's check it out, but let's use hexadecimal. We get 63 right now, right? But if we remove the yield, so it's a normal function right now, we get 33. So actually the function has a different setting in the Python interpreter, therefore the Python interpreter knows when executing this function, return a generator object based on this function. And when executing a function without the yield, just execute the function. That was the main difference internally. Okay, so we should be able to switch to Python 3.7. Yeah, that's here. Perfect. Switch. I'm terrible at typing. Okay, here we go. And so this won't work anymore because I need to do this. And I don't think func code is still in Python 3, but we can check. And I obviously forgot the brackets here. Yeah, they changed it. I don't remember to what in Python 3, but it works pretty much the same. We can actually check what. So it's what was it? It's not, oh, code, that's code. Code, yeah. And this was the code object, and now we can do coflags again. Yeah. Sorry, not dir, because we already want to know the value, but we do not want to use hex on it. So yeah, 43. and 63. So it's the same in Python 3 actually, with this change, but it's no longer func code, it's actually code. Perfect. So knowing this, to call on a generator, you use the generator, like this is the generator, right? And now you do, so let's do this yield 1, yield 2. Okay, so if you call it once and you call it like this next, it will print the first number, the second number, and by the third time it will actually just throw an exception, a stop iteration exception. Python 3. I'm sorry, I will be making this typo all today because I'm so used to Python 2. Oh, did they change this? That's quite funny. Does this work? Yes, it works. Okay. In Python 2, I'm pretty sure they had actually then the generator object had a method called next, but it seems here you don't have to use it. So anyway, as you can see, printed then yielded 1, printed then yielded 2, and then stop iteration exception is being thrown. I'm actually going to start a new console, not in this directory though. Okay. Yeah, it worked like this in Python 2. I wonder if you could do next G. Yeah, you could. So I'm wondering what they did with send, but we'll figure it out in a second, I guess. Okay, back to this Python. I guess I'm going to move it here for now. So okay, so now the interesting part here, what's happening actually in the background, is that once a function becomes a generator, it actually becomes its own fiber. So just the presence of a yield keyword inside the function code, inside the function's body, already means that it's a fiber. So when running the function like here, what we are actually doing is we are setting up the fiber and it's returning the generator object. And the fiber is ready to run. We get a handle to it. The handle to the fiber, the descriptor of the fiber, if you will, is the generator object, and that's our interface to it. Now, going further, the next is actually means, yeah, please switch to that fiber, run it until it yields, and then go back to our main fiber. Let's call it a main fiber. So yeah, in Python, basically like next something, next generator means switch to that fiber, with G being the fiber, and we get switched here at the first time we executed the first time, and then this says return the value, like communicate the value 1, but to like the main fiber, to whatever called next, and at the same time switch to that fiber so that main fiber, and in this case is the main fiber, can continue execution. It doesn't have to be the main fiber, whatever fiber actually well switched to this generator, right? So yeah, that's basically how it works. And this has it has some pretty cool consequences, because what you get by creating fibers or creating new threads is obviously that it has its own context which is running through. So if it wants to sleep, for example, like somewhere in the middle of the function we want to sleep, we just call the yield, right? And then the main thread at some point will wake us up, will wake our fiber up, but we do not lose, after the waking up, we do not lose the context. So if this would be like some function which does some calculations, then waits for data, like yields the partial results, waits for more data, and then executes some more code, and we would set up some really complex context here, like variables, lists, objects, you name it. And then without this like yielding mechanics, if we would want to suddenly just return from that function, wait for more data, and get back to that function, we would have to store the whole context somewhere and then load it from there manually. That means quite a lot of more code. You would have to probably create a class around it, put the our context in the class variables and so on, and it's way more code, and here it's way easier to actually do it. But what we have here is really simple right now, right? It's not really there's no scheduler. Like, I'm switching manually. I'm like saying, yeah, run this fiber. I'm not really doing anything else. So what we could write now do is we could write our own scheduler, like a super simple scheduler which takes some jobs and then actually waits until the job is running. So let's try to do that. I'm going to need some example. Oh, before we do that, there's one more really cool thing which I have no idea how to do in Python 3, but we can try to figure it out. You can see yield here actually sends some data, right? But yield can also receive data from outside. So from outside, we can actually pass something to this fiber. And you usually use it like this, like, I don't know, like v, and then yield in brackets. So when it wakes up, when the fiber is being switched to again, v will be assigned by whatever yield returns. And I guess we can, let's say it's an integer and we put it here. So we run it for the first time, and then it yields, and then when we run it the next time, we actually need to send the data. And I have no idea how to do that in Python 3. So let's do dir on g and run it. Okay. Okay, it requires that it gets done. That's correct. There should be something called send. Yeah, it is here, send. So g.send42. This is the data we sent to that fiber, and at the same time we actually switch to that fiber. So it's like next, but next is basically the equivalent of this. This is next. Send none. But again, it's send and switch to that fiber. So let's do that with 42. And yeah, as you can see, it received the data. It actually outputted 42, and then it like went further. So yeah, that's pretty cool. So okay, let's do the scheduler now. Let's create some like tasks or whatever. So there will be task number 1, which is going to I don't know. Let's just keep it. Let's just do yield here and yield here. Then let's do task 2, which will do something similar. It doesn't really matter. And to complicate, because currently we're just yielding, right? Which so we need to yield for a reason. So let's also add a reason for yielding. And let's do that after I code already some. Sorry, I already code some of the scheduler. So okay, we have these tasks, and now let's make a list of tasks. So let's call it list of tasks, because why not? And let's insert task 1 here. And let's insert task 2. And the idea is that we will be using this list. We will be calling, we'll be popping the first element, calling it, and then the second element, and then whatever is being added to this list of tasks. Can you send data in a for loop? I actually have no idea. That's a great question, mister. I have no idea. I never used it in such context where the for loop actually would send data. Maybe somebody smarter is on the channel and could answer that for you. Okay, so while the list of tasks isn't empty, so while list of tasks, we get something from the task. So that would be t pop 0. That means remove the first element and actually return it. Now it can be one of the two things, the thing which we return. It could be either a generator, or it can be a function. And in this case, it's a function, right? If we would, because we didn't call it yet. When we call it, it returns a generator, but currently it's just a function. So if it's just a function, we basically call it. So if import types, yeah. If type of t is types func type or function type, what is it? Func type or function type? I don't remember. Python import types, the types. It's function type. Perfect. So if it's a function, then just let's just call it. So r being returned value, and we call it without any arguments. Now, r could actually be a generator, right? So let's if it's a generator, we might want to call it in a second. Therefore, what we are doing here is if the function returns, because we might have functions here which are not generators. So this isn't run in its own fiber. It's just like task free. It just prints and exits. It's not a fiber. It doesn't spawn a fiber. It doesn't return a generator. It's a normal function. Here, let's do 2 and 1 so we can differentiate these. Okay. So if it didn't return a generator, then we continue. If type of r is not types a generator type, then we just continue. We don't care. Otherwise, we actually do this. Yeah, we override the task which we got with the generator, because if this was a function which actually is spawning a new fiber, that means it wasn't really executed, and we want to execute it. We want to give it some CPU time, which means that yeah, we'll have to execute it because it's a generator. So at this point, we can assert that type of t is types. Is assert actually a keyword? Yeah, it's a keyword. Okay. In Python 3, I wasn't sure. So we assume right now that t is a generator type. Therefore, what we do now is we actually try to run it. So we do next on it. Next t, and it might return something too. So let's call it red, like just to differentiate from r. It might, if it's finished, right? It will actually throw the exception called stop iteration. That means that's it. Like, there is no more work to be done by this generator, so we just continue. The return value we will use later, but what's important right now is that if there was something, if it didn't throw the stop iteration exception, then the fiber is not finished yet. It still has things to do, therefore we need to re-add it at the end of a list. So we do list of tasks, append t, because that's the task, that's the generator. So yeah, this is basically a super simple scheduler which goes through the list of tasks, and if the fiber hasn't finished yet, it re-adds it at this task. We can what we can do is actually we can print the list of tasks here. We can print t and the list of tasks, so we know what's going on, and now we can run the code. Yeah, the typo. I told you I will make it. Type C. That's a typo. My mistake. Okay. So yeah, basically, first it popped the function task1 from the task list, and the task list only had the function task2 there. It called it, and then it got a generator in response, and then it did next on the switched to that fiber. So we went from the main fiber to the other fiber, and it printed function 1, and then it yielded nothing, right? It yielded none. So given that it yielded none but didn't throw a stop iteration, at the end of the loop we added that thing to the list, at the end of the list. Now this list had already function, task 2, and this is what was function task 2, yeah. And this is what was returned here after popping, and the generator object, as you can see from task 1, is still on the list. So we call that as well, and yeah, we are basically like having two generators now, and we are calling them one after the other. And at some point, well, suddenly both task 1 and task 2, after the last yield, they finish. So they finished, and that's why the program exits. So this is a super simple scheduler for fibers. Now, it doesn't allow us to do any fancy blocking stuff. It just yields. And the problem here is that that fiber is being woken up as soon as possible. And we don't really want to wake it up as soon as possible. What we want to do is we want to, for example, sleep for 5 seconds. And if we do this, like for example here, we want to time sleep 5 seconds, right? So if we call it, then we just blocked the whole system. Like the whole system, by the system I mean the whole scheduler, because at this time, this didn't yield. No other fiber could get the CPU time. So yeah, it blocked everything, like this stupid sleep. And it could be like 500 or something. It could be blocking the system for a while. So this is an important thing when dealing with fibers, is actually that if you do by accident a blocking operation inside a fiber, all the other fibers are not being run. And in fibers, what you want to do is you want to yield with each blocking operation and then be woken up when the condition is completed, or data, like for example, data is ready, or the sleep is waking up. So yeah, we need to do a sleep, which actually is will wake us up at some point. And to do that, let's create another function, which will be, and this is where things get funny in Python 2, and I hope in Python 3, from what I know, due to the added syntax trigger, it's actually better. So yeah, we add my sleep, or like yielding sleep, my sleep, and the how long do we want to sleep? So like time t. Okay, and what we do here is we don't really sleep. We return some magical object type, which will be, by return I do mean yield, which basically is going to be called by the scheduler, and then the scheduler will act upon it. So, let's assume it's going to be, let's create a new class, like, scheduler request, like scheduling request. There's probably a proper name for it. Is this how you spell scheduling? I'm pretty sure that's not the way you spell scheduling. It is the way you spell scheduling. Okay. Well. And yeah, let's just do like request type and request args. Yeah. Self type, request type. Okay, let's do type. We are shadowing the function named type, but we don't care. This is fine. Type and self args. Type. Type is a function, or is it? Whatever. Well, whatever. Okay. So, and here we return or we yield. Let's assume we yield actually the scheduling request, which goes like this. Type will be sleep, and args will be like time of sleep, so time, and it t, basically. So here is when we actually enter the world of herd in Python 2, because in Python 2, calling this mySleep, like let's call, just replace it, like mySleep, this will return a generator. And what we, because, well, this is a function, as I told you, if a function has a yield keyword inside it, Python will add the flag, and when calling the function, it will return a generator for that function. A generator for the new fiber of that function, actually. So, yeah, we just created a new fiber, but that's not what we want. What we actually want here is that we want from our fiber to yield. So we want to combine these two things. And I'm sorry for what you will have to witness now, but you have to actually do something like this. For something in my sleep, yield. Yeah, this is what you have to do in Python 2. In Python 3 you don't have to, and we'll get to that. So what this does is it basically like runs the generator, and the generator returns this, and it actually yields that thing. And we might, you know, have like several layers of that. We could actually cheat a little and do return here, but that would only work for in some cases. So let's just go with this for the time being, okay? And okay, and here we go to the ret type, like here, right? So if type of ret is actually the scheduling request, then we can act upon it. We can, well, start by actually just printing it out. And let's see what happens. Okay, yeah, we got the scheduling request here. So, by the way, 500 is too much, 5 seconds is fine. So, if we get a scheduling request, then we check what type of scheduling request is it. So, if it's actually scheduling ret.type, if it's actually a sleeping request, and we need to, well, there are only a couple of types of requests, and but sleep might be, we could generalize it. Actually, we could have here like return some function which would be called to check a given condition, but let's go for this kind of support for now. If it's sleep, then we create a new list of sleeping tasks, a list of sleeping tasks. And the list will have a different format. It will have a tuple with the wake up time, and then whatever the task is. So like task, like it could be a generator, a function, whatever. In our case, it's obviously a generator, right? And we know that it's the T generator. So in this case, we calculate the wake up time. So wake up time is going to be whatever time it is now, so time, and to this we add ret args from time, the argument, right? And having this, we add it to list of sleeping tasks. We do append, sorry. And we add a tuple, wake up time, and the task. And in this case, if we've done it, we are not appending the task to our list. We remove the task from this list, which means we do continue here. What that also means is it means that we should not exit when this list is empty. We should exit only if both lists are empty. So if there's any task left on one of these lists, we should actually still run it. And another thing which we should do is if not list of tasks, like list of tasks is empty, in that case, we, there are actually two cases, right? The list is not empty, in that case we do this, else it is empty. And if it is empty, we check, well, we know that the list of tasks is not empty, but let's check just for the sake of it, and let's do else assert still the same in Python 3. Yeah, still the same, like whatever you type here gets reflected here. Okay. So in this case, our task will be, well, it might be, but it depends on what time is it now. And actually what I would do is I would also sort it a little, but let's do a different thing here. let's go with for t in list of. Yeah, this actually should be an ordered list, a sorted list, but yeah, it's just. Okay, just a small optimization, doesn't really matter in our case. Here, if we actually get two things, right? We get the wake up time, and we get the task. So, and we should cache now time. Okay. So if wake up time, if it's time actually to wake up, so if it's larger than now, we need to. We actually have our. We can do a break. We have our thread already. And otherwise, if we reach here, we can do an else, and we can, let's just sleep. There is no sense wasting CPU cycles. Let's just sleep for 10 milliseconds and then to continue. Because we know at this point that the list is not empty, but no task was ready to be processed. And if we do a break here, please note that the t has been assigned here. So this t and this t, that's the same t, is being assigned magically by this, so it will be processed here. So having something like this, we can actually try to run it. And okay, this doesn't work. Why doesn't it continue at this point? Let's try something else. Okay, where's the beginning of this? Okay, let's see what happened. T. So the list of tasks is empty, and we get here T. Now task 1. Why do we get even here? We shouldn't get here because this does a break. So if wake, no. If now, sorry, that was my mistake. Yeah, this is where it should be. Okay, yeah. And now, as you can see, okay, it almost works. Why didn't it fully work? It almost works because it's it executed the other task. So where is this? Let's try to analyze it at this point. It executed task 1 and task 2, and then it executed task 2 again. So task 2 finished. It ran this and ran this. And task 1 actually is sleeping. So we finished all the tasks. The task 3 is finished, actually. No, because I never added it to the list. So let's add task 3 as well. Okay, so all the other tasks finished. And the only thing we have right now is we are waiting for the sleep to finish. And only when the sleep finishes, then our task will be run. Oh, I know what's the problem. I didn't pop it. I should have popped it. So how do I... okay, let's do this. Bits of sleeping times. Okay, now it's better. No, now it's better. Because I forgot to remove it from list. That's the problem of the list from the list of the sleeping tasks. And not enough to unpack. Okay, now it works. All the tasks have finished, and the only thing we are waiting for is for this task to finish. So it works now. Now, we do not like this syntax, and it turned out, it seems that in some Python, they actually added, like Python 3 something, they added another syntax for the same thing, and it's called yield from. So we can do now yield from mysleep5, and it means exactly the same thing. It's like just a syntax trigger for this. A really nice syntax trigger. Thank you for introducing it. And if we run it, it's exactly the same thing. We get exactly the same functionality, right? Nothing changed, it's still the same thing. And from what I know, and I will just check it right now, I never tested it, is await means actually the same thing in Python, the newest versions of Python. Outside of an async function, I do need to write async here, it seems. but it doesn't work the way I intended. So I guess await means something else. So, but let's stay with this for a while. And now, well, actually no. Actually, I think that's the point I wanted to get with this syntax. And now let's try to figure out what does async and await mean in the context of this, because it can be used for the same things. And just again, it doesn't have to be about sleeping. This could be like, I would like to wait for some data to be processed, right? And I would like the data to be wake up. I would like this thread to be woken up when the data is already, thread fiber would be woken up when the data is already processed, or when the data is ready because it's being fetched from the network and it's a super slow process, and so on. So, yeah, let's find a pep related to pep Python, pep, await, and async, and see what's that. Okay, so I guess that would be one of it. There's another, and another. Sorry. Okay. Let's see what was the syntax that they were aiming at. When it was it? 2015, 16. Asynchronous generator 16, and async IO. Yeah, this is a library, by the way, which does the stuff I kinda showed you. So yeah, this would be the scheduler, right? And this would be the way you actually write your code. I guess we can switch to that library in a second, but I would still like to figure out what does both these keywords, what do they do? So I guess I'm going to open another code and experimental tool. This is where the point I'm actually reaching the subject of the stream. I guess before we get that, let's see if there are any questions related to the topic. Okay. Okay, so we already answered this one. Przemek writes, I think some operating systems have multiple layers of threads, some inside user mode, out of the box. Yeah, for example, Windows, it has fibers. It has like create fiber and switch fiber and so on. On Linux, you can use a pthread library, and it has the same thing, I believe, like also, well, different naming, but the same stuff. The best advisor writes, couldn't you fire up one thread that checks all pending operations and gives a result to the main thread when one returns? It's actually a cool question. So it's like this. Depending on the architecture, sometimes it's exactly what you want to do. So you might want to fire up another thread. You might want to do polling of operations, like, hey, did this operation complete already? Did that operation complete? Did maybe another operation complete? There's another way to do like standard I/O on Linux and Unix operating systems. Like you could do a poll and give it quite a lot of file descriptors, and then if any data is ready on any of the file descriptors, it would unblock. And that could also be useful here, just not to have a thread running all the time, but the thread could actually just do that and sleep. Select also does a really similar thing in select the glibc function. So yeah, you could do that. Now that still means you do context switching on thread level, which is kind of tricky and slow. So that's why you usually don't do it unless I misunderstood your question. It's not that you usually don't do it. You don't do it in case of when you want to use fibers, right? Another thing for fibers is, by the way, that it's super simple to span a fiber. Like you just allocate some memory for the stack, for the context, and that's it, right? and in terms of a thread, that's actually asking the kernel to do something, so that's chatting with the kernel. Spanning a fiber is purely a user mode thing. I'm not sure I actually understood your question there, Supervisor, so yeah, just feel free to follow up. Okay, and there are a couple of random questions, so let's go through them as well, only 5, so yeah. Inject IT says, after getting input from address pins, are bits from 8 chips combined in RAM to make 1 byte of data? I don't know if the question makes any sense, but I don't know how to ask it the other way. So when it comes to RAM chips, right, you usually define them by the width or like the size of data they are storing. And for programmers is like obviously 8 bits, right? You store 8 bits of the data at the same time. It's not so obvious on like the actual electronic level. If you go through like DigiKey or whatever and you look at RAM modules, the width is, you can find like 10 bits, 13 bits or whatever. We can actually do that just for fun. So DigiKey. I'm not endorsing DigiKey, but I do like them. So yeah, let's go for RAM, memory, modules, like memory. Let's make it a little bigger. And yeah, if you look here at the electronic parts, right, you do get, yeah, the memory size is usually like, for example, 32K times 8 bits. So that's a kilobit, by the way, 256 kilobit. That's just one dice, right? So you usually on the RAM module in a PC you have multiple. And I'm not saying these are for PCs. This is SRAM. It might be used for, I don't know, when you're designing some stuff. However, we can actually, I believe, sort through the memory for the width. So let's just adjust this and see what happens. Okay, memory type, nothing, perfect. More filters. I want to get, okay, volatile. Series doesn't matter, manufacturer. We want in stock, apply filters. We want more filters, yeah, and we want, this is another thing, I'm going to get back to that in a second. Where are the, oh yeah, here it is, the memory size filter. And yeah, as you can see, like sometimes you get 36 bits of data at the same time, or like 16 or 18 bits of data. So we programmers are used to 8 bits of data, but yeah, I mean, like there are chips out there which can give you, after you give the chip an address, it can give you more bits of data, like for example 36 bits of data, right, at the same time, or like 24 or whatever. There are like variations of it. 8 bits I think is the most popular, but there are other variations as well. And the other stuff is the interface. Like parallel would mean that for 8 bits, right, you have actually 8 pins, and if you give it the address, the data will at some point appear at the pins. Like the super simple like ROM or RAM devices have like 8 pins for the address. You put the address, you wait a clock cycle or something, and then you just read the output of the pins, and that's your data. But you can also use like SPI. SPI is a super simple serial protocol, which means that you have only 1 pin of data. I think in SPI, I don't remember it, but yeah, I'm confusing it, I think. No, it's okay. I was thinking of the right thing. It actually goes in duplex mode, and you have the connection. So this would be your computer, whatever, and this would be the RAM chip, right? And this is a clock for clocking. Then you send the address using the MOSI, like master out, slave in, and you read the data using MISO, like master in, slave out. So it would actually using the serial protocol, with each clock send you 1 bit of information up to 8 bits after the address you requested. So here it's just 1 pin, right? 1 pin for the input data, 1 pin for the output data, and this is probably for enabling, and this is for clocking. So that's basically how it works. If you look at FPGAs, it's actually also pretty obvious. What is more interesting is that one RAM dice could actually have multiple interfaces to it. So you could have like one writer and one reader interface to it, which makes sense if you start to think about it on low level. What can you use to create mobile applications for Android, iOS, and Python? Is it a good idea? I actually have no idea. I never created a mobile application in Python. In all honesty, last time I created a mobile application, that was 2008, 10 years ago, and that was still in Java 2ME. So I don't know. I'm sorry, I just don't know. Is it a good idea? It's a good question. Depends on the support, I would say. If Python is really well supported with, for example, Qt, right? The Qt library you can use it for Android, then why not? Otherwise, I would stick with the default technologies on a given platform because they're better supported. Przemek says, I think on Intel chipsets, SPI is used to flash the BIOS. That's... are you sure about that? Because there's something called the System Management Bus, MBus, and that's actually I2C, I2C protocol, if I remember correctly. And that's used for several things on the motherboard. I would expect actually for flashing BIOS as well, but perhaps you're right, perhaps it's actually SPI and I'm misremembering. How RAM diagnostic tools work if they are also in RAM? That's a good question. Actually, the ones I use, I've written the super simple ones, just written some stuff to memory and then read it back and went through all the RAM. You can actually, using the system management bus, get information about a given RAM module, but I'm not sure you can do much more, in all honesty. And they don't have to be, technically they don't have to be in RAM. There is a way on x86 at least to store the code in the CPU cache and run it only from cache without the code residing in RAM. This is how BIOS actually initializes. When BIOS is on ROM, right? And it doesn't even have the RAM memory control initialized on the motherboard when the PC is starting. So the ROM actually, the code which is executed on ROM, it's actually compressed usually, changes some setting on the cache, so the cache acts as RAM. And if you think about it, that makes a lot of sense. It is basically like super fast RAM, right? And some BIOS code might be copied to it or decompressed there and is running from cache until the RAM controller and RAM modules are initialized. Only then you can actually start using the system RAM. So it's not like the code has to be run from RAM. It can be run from CPU cache. It's just not trivial to do it. That being said, I did see some papers some time ago how to do it on Linux. Like how to run. You obviously have to block one core only for your thread and do some other magic, but like kernel level magic. But yeah, you could run your code only from cache, which is quite... If you think about it, it's quite interesting, right? Because no debugger will have access or visibility into the cache because it's private, super fast SRAM of that given CPU or like flip-flops or whatever that is. And yeah, there is no way to read it. So that's why hiding code in the cache is also, was I think in that paper at least. I'm not sure if that was ever used in the wild. Okay, Hexploit writes, back in the days you recommended Python and C# as starting languages to start programming. After many years, would you recommend the same languages? I stick with Python. I might add actually JavaScript to the list. JavaScript is a funny language, and it doesn't it doesn't teach you proper programming. I'm sorry, because it's weird. I mean, very weird choices have been made when designing that language, and you program in it in, surprise, surprise, asynchronic way, right? Like, this is a magic thing in Python, but in JavaScript, this is the way you have to think about programming. That being said, if you're just starting programming, you don't care about that stuff. That's the thing which, like, your friend who is a senior programmer tells you that, yeah, that's like, not good. And that's a bad design choice for the language, but you actually don't care. And in JavaScript, you can see the result really quick. You can see with your eyes, like, that a picture is moving. If you click on an interactive button, something happens. JavaScript with HTML is really cool for beginners, I think. Yeah, C# I would still leave on the list, maybe alongside with Java, but these are like secondary choices, I would say. How fast internet connection do you have, and is it fiber or copper internet? I have 500 megabit download and 50 megabit upload, and it's a cable connection. Is the DNS pingback the result of a vulnerability at X forwarded for an HTTP request exploitable? What? I'm not really sure what you have in mind. If you could follow up on it, like, I think I might be getting the idea, but if you could actually follow up with me on that. Okay, one more question, and then we get back to the subject. How hardware assign I/O map or mem map addresses to specific chips? How BIOS does it? How to be sure that on some address I can communicate with specific chip on the motherboard? It's an excellent question, actually. I don't fully grasp it yet, so I cannot answer your question at this point. There's some magic there, as in, like, the hardware actually has quite a lot of choice on that. I think I/O map is actually a little simpler, because I'm not sure devices nowadays can actually use any addresses they choose. Like, that was the norm on the ISA bus, but I'm not sure about the PCI Express. I think you only rely on either memory mapped I/O or like some standard PCI I/O ports. But yeah, I'm not sure, in all honesty, yet. I don't really understand it. So let's get back to that in a couple of years, when I have a better understanding of what is going on the motherboard. Okay, let's go back to the topic. So I was trying to figure out what to do with what is async and what is... wait, so okay. Let's do async def asdf and return 5 and see what happens. It should actually complain that I'm trying to return a value, but maybe that's a thing, I don't know. And let's call it and let's print it. Okay. Okay, runtime warning, coroutine ASDF was never awaited. So it seems they added actually something more than a syntax trigger. It's now a coroutine object, it's not really a generator anymore, so it seems it's... we do not have to abuse one mechanism, like the generator mechanism, to actually do coroutines, which sounds really cool. And it did return a coroutine object. What is a coroutine object? Let's do theater on it. Okay, so it has some stuff like CR frame, CR origin, CR running. I can do a send to it, so that here you don't really see it, now you can see it. So it doesn't differ that much, it seems, from a generator object. Let's do like... it's a routine now, so let's do it like this. Okay, I like that warning. Okay, so let's do r dot. Can we do next on it? That's a good question. Can we do next on it? Coroutine object is not an iterative, so we cannot do next on it. Can we do send on it? Well, there was the send method there, so let's do. See what happens. Cannot send non-value to just started coroutine. This is, by the way, the same thing which happens on generators. You cannot send a value to something that didn't yield yet. So that's the same. Okay, so if we cannot do a next on it, how do we run it? And I guess await it will be the answer here. We can await for it. So let's do just that. Let's do k equals await and ASDF. Sorry, that's R actually. And print k. Let's see what we get in return. Await outside of function. So we cannot do it like this. Is there a function called await? There isn't probably a function called. I'm quite curious how to get this function to run. That's what I'm trying to achieve right now. Let's do dir once more on this object and see. Sorry. Okay, k is not defined. Okay, so we get back here. Now, at some point I really need to take a look what is in all this stuff, because it might be quite interesting. Async. You say that. Wait, what? Okay, this is the moment when I RTFM, I guess. So I don't want to use the library yet, and I don't want to look in the library. What do I do here? Async for okay. I async for okay. Wow. Do I really do async? No, that's not that syntax. So I guess that syntax didn't work out. Let's check this. Yeah, by the way, if you're interested in like languages in depth, then you, in case of C++, you obviously need to read the C++ standard, but in case of Python, usually you want to go through PEPs, since all the proposals and also the implemented proposals are there. A next. Oh, hello there. Is there such a thing like a next? A next? No. A iter? No. How do you run it? Async. But seriously, can I just await? Wait. ASDF. Why do I have to use the function? Async function, okay. Okay, so yeah. It seems they really want us to use the async IO. Okay, let's use the async IO in that case. I'm not happy about having to use it, but we can check in a second how is it implemented. Okay, there is the event loop and run until completion. Yes, let's just copy the example. Completion asdf, and then loop close. Let's see if this works. Okay, so this works. Now let's do print asdf. Let's do how was it? Await async IO sleep 1 second, and then do xyz. Right. My favorite typo. Okay, so this works, right? But how does it work? This is my question. So, for example, what is loop? Loop is window selection, selector, event loop. Okay. Python. About the async IO, get event loop. Okay, so this is the loop and the loop object, and then we run until completion. I'm really curious how does it work, and that's why I'm not really interested how to use it. I'm interested how it works. If I would like to do this manually, how do I have to do it manually? Okay. Sometimes console like Konemo breaks for me and doesn't want to copy paste everything. Okay, so loop run until. This is a bound method base even loop. Okay, so now we are going to try to find the source code of this. Question number 1 is async IO. Oh, it's actually in Python. Perfect. So we are now in the async IO directory, and it says it's base event loop. So base events, I guess somewhere here. That's a pretty huge file, by the way. Okay. Well, it supports quite a lot of different events types, but that's expected. Let's look for this method. It's a callback, yeah. Okay. Oh, it introduces the concept of futures. That's cool. So we give it a future. Sure, future, new task. Add done callback, okay. Self run forever. Exception, okay. Run forever. So what happened here is that where does it use the future? Okay, it checks if it's new task, not futures is future, okay. And it's ensure it's a future. If it's a new task, then whatever. Otherwise, future add callback when it's done. And then it does run forever. It's a pretty similar code to what I've written at the beginning of the stream, by the way. Okay, what does run forever do? Run forever, hello. Something, something. Okay, self run once. Set running loop, run once. Run once, what do you do? Okay. That's quite a lot of code, by the way. I'm looking for like a magic way to actually run it. Handle run. Is this it? Can I just do like k equals asdf and k dot run? I'm pretty sure that's not it though, but let's try it. No. Let's do the again on it. Okay. No. Yeah. What do we have here? CR running, CR origin, CR code. Oh, by the way, can I just like do K like this? That would be funny. Coroutine object is not callable, so I cannot do it. Can I do for something in K print something? Coroutine object is not iterable, so I cannot use that either. If anyone knows, by the way, on the chat, then please let me know. I seriously don't know, and I'm quite curious. And it would save us some time. Okay, so another place to look is actually to look at the coroutines implementation. To look at the coroutines implementation, I would have to get the source code. I don't have the source code of Python 3.7. I do have the source code of previous Pythons, though, quite a lot of them. So let's go with Python, this one. Python coroutine, something like this. 3.6 is the source code I'm going to look for. I know you cannot see it, but bear with me. Okay, so from the source code. Okay, so this is a decorator. Okay, head over. Gen, is there such a thing as gen? Yes, but this is a generator-based coroutine. Not really what I would like. Yeah, it uses the same syntax we tried, so this is not helpful. Radu recommends checking David Esley on async and await, because it seems there's a good video about it, how it works in the background. So totally check it out. I'm going to leave it for myself as well, but I would still like to figure it out. By the way, so looking at this coroutine, is the built-in? So async def a pass like nothing, k equals a, dir k, and class k class coroutine. Is it a built-in class? Okay, here we go. I can raise a generator exit inside coroutine. I can send something. Return an iterator to be used in await. Oh, okay. Object being awaited on or none. Okay. So, what happens if I do actually like k.await? Method wrapper, perfect. Okay, so it returns a coroutine wrapper object. Let's grab the wrapper object, m, and what does m have for us? We can do what can we do? I don't know. Can we do next on m? Oh, we can do. Okay, so that might be how we are supposed to handle it on the low level. So we have this, and now what we want to do is we want to do await, and we get something, and then we do next on m. Then we print sd like this, and then we do next on m again, and assuming that this await will actually switch the fiber, it should go like this. ASDF should be printed due to this next, then this should be printed, and this should be printed due to this next, and stop iteration should be thrown. Is this how it will go? Await wasn't used with future. So something worked. We got it running, but not to the full extent. I'm quite curious what was returned here in the first place, and what was returned here in the second place. Future pending. We have a future. Okay. What's a future? Well, I know what's a future. It's like this. At least in JavaScript, there's basically a class which you get an object of that class, and you're supposed to use it for signaling when you do something, or the other way around, like the class tells you, the object tells you if something was complete. So it's updated asynchronously from your thread, and you can actually interact with it to check if something was you can interact with it to check if something completed. It's pretty normal in asynchronous programming, by the way, but you get objects which you query from time to time to check if some action, some asynchronous action going on in the background has been completed. Okay, so we get a future here. Okay, so that's f. And what, dear f, what do you have for us? We can cancel done. Okay, we can tell it done. Totally. F done. We're done. Okay, it said false. Await wasn't used with the future. Why do I need to use await with the future? Yeah, it seems a little more complicated than using generators. So, because I guess done returns actually if it has completed, not whether, for us to mark that we did something good. So let's call await on the future and see what happens. We get an iterator. Okay. I'm not sure if we are not going in the wrong direction in this case. And let's see actually what happens if we call the iterator. Await wasn't used to the future. Yeah, it seems a little more complicated, but they added some things. They expanded on the mechanism of the previous coroutines that existed. So I guess it's a good point to actually call it a day for today. And I'm going to probably dig in a little more to how everything works, and then we can have, I don't know, a 15-minute follow-up on it on the next stream, or after I'm actually finished with it. Because it seems that there are quite a lot of cool stuff here to look into. I guess the bottom line here is that while you could use yield and yield from as manually, like we did here, right? To use async and to use await, it's actually better to use the loop because it's probably quite complicated as we saw to operate on it. But we'll get back to that subject later on, so expect part 2 of the live stream. That being said, from what we see, it uses the same principles, and yeah. So let's go to questions, and then let's wrap it up. Okay, you heard that the major web browser makers like Google, Mozilla, Microsoft want to disable the old version of TLS. What do you think about it? Well, if it's like this, I'm not an expert on TLS, okay? So just from what I read is that there are some things which cannot be fixed. Well, were not fixed, but there are weaknesses in until TLS, and SSL is the new thing. So yeah, use SSL, not TLS. Disable TLS. That's a good thing to do. Like deprecating all the mechanisms is a good thing to do. So yeah, I think it's a good choice. When a fiber is waiting for data, when a fiber is waiting for data, allowing the other fibers to run, at what point will the first fiber be brought back to execution after the interrupt for data received is sent? Well, it will be brought back to execution as soon as the user mode scheduler which you have brings it back to execution. So that everything depends on what kind of scheduler are you using in the end, and if you have something like priorities, or will you just add the, like for example in the code which I've written, right? The task lists which are ready were on the first list which I created, and these had priority. And only if that list was empty, I would grab a task from the sleeping threads to check if something is ready for execution there. And so I didn't give any priority to that, but you could do the other way around. You could check first if there is a new sleeping fibers already ready and switch to that, and only if there are no sleeping threads which are ready, go to the usual task list, like the other things which you have ready, already. I think actually our approach was a little better, but yeah, I mean, you select basically based on the code and the logic which is written in your scheduler. You select what is going to be executed. What's the font name of the font I'm using in QEMU? That's a pretty default font, like Consolas or something. Let me check. Yeah, that's Consolas, like standard Windows Consolas. Why don't I use IPython? Because I always forget to execute it. I have, muscle memory for typing Python, but I don't have muscle memory for typing IPython. If I would change do an alias or something, I would use it, because I like it. Are you on the super singular isogeny hypertrain? I don't know what that is either. That sounds like interesting. Super singular isogeny key exchange. It's a Diffie-Hellman key exchange, a post-quantum cryptographic algorithm. Yeah. Yeah, no, I do not have a comment on super singular isogeny key exchange. Sorry. So that's it for now. There will be another stream of unknown subject next week. And at some point I will follow up on the async IO and like coroutines in Python 3.7, but I do need to do some code reading before I learn it. I thought it would be a little easier in all honesty, but during the live stream we could like just take a look and it was all syntax trigger, but it seems it's not syntax trigger, so I learned something and I'm quite happy with that. But we'll have to you'll have to wait until I figure it out before I can say something more about it. Cool, so that's it for today. Thank you to my moderator KrzaQ for being here, and see you next week. And I wish you a pleasant evening, and I'm going to leave you with some music. So yeah, that's it. Bye bye.